let's talk about readbacks first. And what is a readback? A readback is where we can read the data from anywhere in your program, which is a really powerful tool. You can choose a place in your program and say, okay, tell me what the data is right now. And of course, it just reads that one sample period and sends that to you when you click go and it reads it. So it's not over a bunch of sample periods, it's literally one sample um, at that particular moment, right from the core. So very powerful feature. In we started this feature. It was a bit of an innovation when we designed this into the first Sigma DSPs, the Sigma DSP 100 core, but it was done in a bit of a cumbersome way, which I'll go into more in detail in a second. So when we went to the Sigma 200s and Sigma 300s, we improved them quite a bit. And um, in the Sigma 300s, well, the Sigma 200s is 28 bits, so we get the 28 bits. In the Sigma 300s, it's a 32-bit core. And so I went through the trouble almost here of, I say almost, of drawing a bunch of blocks, pigeonholes for a 32-bit number. And I counted the bit numbers, bit number 0, bit 1, bit 2, bit 3, etc., all the way up, bit 28, and then I ran out of whiteboard. 29, 30, 31, 32. So you got to imagine I had to stretch the whiteboard a little bit there. So we have the whole 32-bit number. And up here, and I apologize for the reflection, it's a little bit out of control here, the lighting in here. It's my poor representation of a computer, of a laptop, running Sigma Studio. And I have a little USB cable. There's a USB-I interface, and that comes into the eval board, the actual DSP that has the core, the number that's in the core, 32 bits that the program's running in the core. Um, so when you click read back, it at that moment it'll go and get the core. I mean, what all the readback is, by the way, is an instruction in the program. It's a memory location. It's a 32-bit memory location, right? And as the program code is, you have code you're executing, et cetera, et cetera. And as it gets down to where the readback is, it's going to say, okay, dump the result of the last, take the results of the last operation, whatever that was. That's going to be, if it was an add two numbers, and then we're going to store it at a particular location. So this is the addition, you know. So we're going to store the addition into that memory location. And then the next instruction is going to be the readback. The readback is going to say, okay, take that number you just stored there and put it into a memory location for the readback. So this is an actual memory location that the program will store it in there. Every sample period, it'll update whatever that addition was, it'll update it every sample period. And then at any point, the USB-I, you can go in Sigma Studio and say, click on the read button. And it will go and say, what's stored in this memory location? And it'll take that memory location, the 32 bits, and bring it up and display it for you on the screen in a little read back box in hex or um, in a fixed point format. I'll show that to you in a little bit later in this video. But anyways, that's all it does. It grabs that memory location and puts it up on the screen at that particular instant. If you set the readback to continuous readback, it isn't quite continuous because every sample period, if it was at 48 kilohertz, that'd be 48,000 samples a second. No, it doesn't do that. I believe it's every 10 milliseconds. It'll go and it'll read and show it to you and read and show it to you. So it still can miss a lot of values, but it gives you somewhat of a continuous readout. So that's how it works in a Sigma 300 core and a Sigma 200 core, except it's only 28 bits. But there will be a memory location that'll get updated, and the read back function in Sigma Studio, all it does is read that memory location and bring it up. Uh, that's how that works. Now, in the Sigma 100 cores, it's a lot more cumbersome. There's a thing called a capture register, and it's set up that when the code you set up a capture register in hardware that when the pointer, because there's an instruction pointer, for which instruction are you executing, and there's only 1024 instructions in a Sigma 100 core, and so at a particular instruction it'll say take the contents of the 28-bit result and put it into a certain register, and then you can read that register out. Well, that register is only 24 bits. That's it. It's not 28 bits, it's 24 bits. So, um, therefore, the read back register equals 24 bits. So the memory location goes from 0 to 23. It's only 24 bits. That's what gets transferred up to the computer and gets shown. This is why in the box, in the software, when you select for fixed point, it'll say 5.19. It won't say 5.23. It'll say 5.19. You add those two up, it's 24 bits. So what this is telling you is, okay, we're taking a 5.23 number. So here's the 5, 1, 2, 3, 4, 5, right? This is the 5. Here's the dot, dot. And then, wait, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, duh, hold on. I started at 28. It's not 28, it starts at 27. It's 0 to 27. So in the, sorry, it's easy to make these mistakes. There's no 28 in the Sigma 100 core. Okay, so 1, 2, 3, 4, 5. We're right to here. Sorry for that. And we got the dot right there. And so we got 0 to 22. So here's our 23. So we have a 5.23 number. Now we're going to have to transfer this into this 24-bit memory location. So what are we going to do? We're going to, since this is a clue, 5.19, we're going to take this 5 and transfer it here. So we're going to take the whole 5. I should stay in red. I'll stay in red. We're going to take the entire 5 and put it in. So this gets moved over. And we're going to not take this bottom 4. We're going to, from here, how to not make this a mess? Here's where I can use the green. Right. 19 digits. If we count it out, it'd be 19. We take that and we move it here to 19. So we're not going to take the bottom 4 LSBs. They get truncated. So when we're doing a read back, we're not going to see these 4 bits. This becomes very important when we're dealing with integers, when we're dealing with cells that use these bits and we want to see them. We're not going to be able to see them. Well, actually, I suppose it's not a bad time to go into that right now. So that's the little secret of the readback in the Sigma 100s. You're getting the significant part of the audio, which is why we chose the 5.19. You're getting the significant part of the audio. You can see the whole headroom. You can see positive or negative. And usually the last 4 bits, when you're talking about audio, that's down in the noise floor anyways. So it's not as big of a deal. But when you're working to control a mux and you want to see what the position is, you got to switch a mux. And you got, 5, 6 different positions, maybe 10 positions. A lot of times it's only 3 or 4, but we're using an integer. So it's 0, 1, 2, 3, 4. It's all these four bottom bits. It goes up to 15. And so we can't see it. It won't show up. This will be zeros. It'll all be zeros. Even though it's changing, this will all be zeros. So what we need to do is take this data in the core, the 28 bits, and shift it 4 bits over. So we need to do a data shift over. By the way, in the Sigma 300 core, we actually learned again, we improved. And there is an instruction in the core to do a shift, a arithmetic shift. That's why that's in the library, arithmetic shift. Easy for me to say. And it's a barrel shifter in the hardware, so it's easy to do, very few instructions. However, it doesn't exist in the 100 core or the 200 cores for that matter. And so we got to do this shift in a smarter way. And so how do you shift the bits over? Well, you multiply by the base. In this case, it's base 2. So if you multiply by 2, we're going to shift over one bit. Multiply by 4, we shift over 2 bits. Multiply by 8, we shift over 3 bits. Multiply by 16, we shift over 4 bits. So we need to multiply by 16. Okay? We multiply by 16, we're going to move these over. Obviously, this is going to clip. The sign won't be right, but and the bottom 4 bits of the 24 bits now of the readback, we're going to see those bottom 4 bits. And this will be an accurate number at this point. So we need to multiply by 16. Okay, now I hope you watched my video about the number formats, because you might remember that in this 5.23 format, we only have 4 bits to represent a whole number, and that goes up to 15, 4 bits. 4 ones is 15, not 16. So we can't take the multiply block. There's a block you can do for a multiply. I can't put a 16 in there. It won't take a 16. So we can't multiply by 16 directly with one block. So what we do is you take 2 multiply blocks, you hook them up in series, and you multiply by 4 twice. Then you get to multiply by 16. So we shift over 2 bits, and then we shift over 2 more bits, and we got it. Then we do the read back, and we're good. So what we do in the program is, let me erase the computer here, is, whatever the result this was, we're trying to read back something. We multiply by 4, and then send it to the read back cell. And this is where you have the read button, where you're going to press the read button and look at the data. And so you multiply by 16 and then send it to the read back. So this would shift the data over by 4 and then shove it into that 24-bit location. So that's the little tricky, dirty little secret there. Sorry about that, but that's the way it is, and that's how we can end up multiplying by 16, get around the problem of only having 4 bits. The funny thing is in the Sigma 300 core, we could put a 16 in there because we have 7 bits. We can go all the way up to 127. So, but we have an instruction to do the shift. So the Sigma 300 core, there were so many improvements to that core. It's an awesome core. Don't forget to hit like and press subscribe. Have a good day.